Hello class. So on this video, we're going to start on section 6.1. Right? So we finished chapter 4 in the previous video. Now we're going to be in chapter 6. So again, this is section 6.1 in the book, and basically we're just going to be covering as many sections as we can until the end of the class. If we reach enough sections that I feel that we've covered enough material, I might include some other things from other chapters that are useful and interesting and that apply some of the concepts you've learned in other classes. But for now, the Laplace Transform, which is the topic of chapter 6, is a very important tool, so we're going to focus on this for now and just see how much we can get out of it. So what is a Laplace Transform? So as it says, it's a sort of transformation. So what are we doing? We're transforming a function. So we're transforming a function and making it into another function. Now, why are we going to be doing this? So the whole point of this Laplace transform for us is to help us solve differential equations. How is the Laplace transform? Which again, I have the definition here. I haven't gone over it in scale. I'll go over it in a moment. But why is the Laplace transform going to be important for us? Well, the idea is something similar to what we did with exact differential equation. So if you remember, for an exact differential equation, you have something that looks like this, an expression of x and y, plus another expression of x and y times dy dx equals 0. And if you remember, if m and n satisfied some conditions, specifically if the partial derivative of m with respect to y was equal to the partial derivative of n with respect to x, then we knew that there was a function equal to some constant where any y that satisfied the differential equation also satisfied this original function, or this function f of xy, and vice versa. Okay? So what was the idea? We were simplifying the problem from a calculus problem to an algebra problem, solving for y in an expression of x and y. So summarizing, the goal of this was simplifying a calculus problem to a purely algebra problem. So can you solve for y as a function of x? And if not, you can just leave it as an implicit solution. But there was this simplification that went on. We forgot about the calculus and went to something that involved basically less structure, which is just algebra. And the idea of the Laplace transform is going to be something similar. We're going to start with the differential equation. We're going to apply the Laplace transform to both sides of this differential equation. And that's going to simplify our problem, hopefully. In particular, it's going to make our differential equation, a calculus problem, go to an algebra problem, just having to solve for a variable. So that's going to be the goal, right? And I state the goal now so you know what we're going to do, because before we get to actually applying this Laplace transform to differential equations, there's a lot of theory we have to cover. So not too much, but a little bit of theory. Right? There's definitely some theory in there. So I don't want us to lose track of why we're covering this. Right? So again, even though there's going to be some work into defining this Laplace transform, defining when does it exist, etc., the payback or the payload is going to be for us that it's going to simplify the process of solving differential equations. We're going from a calculus problem to an algebra problem, similar to the exact differential equations. Okay? So that's the idea. Now, the Laplace transform that we're going to see here, it's not the most general form of it, right? So let's start with the definition. I'm going to talk a little bit about why is this not the most general form, how can it be generalized, and other sorts of transforms. Okay? So definition 1, let f of t be a real valued function, so the range is real numbers, defined for t greater than or equal to 0. Then the integral, defined as the integral from 0 to infinity, of e to the negative s times t times f of t dt is called the Laplace transform of f, provided that the integral converges. So there's a few things to note about this definition. So let me go to the note. Well, first of all, is how do you evaluate an integral like this? Right, so it's an improper integral. So if you remember from Calc 2, how do you evaluate an improper integral? Well, you rewrite it, and this is the first thing you want to do anytime you're computing Laplace transforms by hand, right, is you want to rewrite this integral as this, right, as this integral here. If you remember, this is by definition what an improper integral is. Right? Taking the integral from 0 to infinity is the same as taking the integral from 0 to b, and outside having the limit as b approaches infinity. That's the first thing to note. This is how we're going to be evaluating the Laplace transform. We have to use this definition where we go to a limit. Now, that brings me to the other point, right? Here it says that this is the Laplace transform of a function f, provided that the integral converges. So if you remember, an improper integral doesn't necessarily have to converge. And we can see it more easily if we look at this form of the integral. We're taking the limit of an expression. Right, so this integral, the integral from 0 to b of e to the negative st f of t dt, that's going to exist as long as f of t times e to the negative st is integral. However, the limit afterwards might not exist. Right? So what this is telling us is that we can't take the Laplace transform of every function, right? Because this limit might not exist. Right? So this already is telling us that we have to take some care about how we deal with the Laplace transform. There are only some functions that we can actually evaluate this integral, right? Or in other words, there's only some functions in which you can evaluate this limit. Right? So only some functions have a defined Laplace transform. Right? So you have to be careful how to use this, and you have to verify that this actually exists before you use it. Okay, so two things. So let me keep track of what I'm saying. So first, we said that this integral, or this improper integral, might not converge, right? Might not exist. Right? Because the limit might not exist. Okay, so it's the first thing we said. Second, this means that the Laplace transform is not defined for all functions f. Meaning that you have to be careful how you apply it. And then the last thing I want to note is, look at this integral. So let's suppose that this integral actually converges. Suppose that this limit actually equals something. Let's see what's going on, right? So notice that the integral is respect to t. So when we evaluate this part here, we're going to get an expression, right? We plug in 0 and b. We're going to get an expression that only involves s and b, potentially b, because we're plugging in b for t. Right? So the idea is, since we're plugging b for all variables t's, this expression that we get is no longer a function of t. The only variable left over before we take the limit is our s and b. And after we take the limit, the only variable that's left over is this s. Oops, so actually I don't want to do that because I erased the t. So what does this mean? Assuming that this integral exists, what we're going to be left over, what's going to be left on the right-hand side after we evaluate the integral and then the limit, is going to be some expression involving s and constants. If we want to write that mathematically, assuming that the Laplace transform exists, what do we get? We get that the Laplace transform of a function f of t is some expression involving s and constants, right? As you know, how we write that in this class is as a function of s, right? It's the same thing. And that's the notation we're going to use. Okay, so we're going to use lowercase letters for functions and uppercase letters for the Laplace transform of functions. So that's the last note. If the Laplace transform of a function, let me make that more clear that it's a lowercase f. So if the Laplace transform of a function exists, it is an expression involving s. In other words, we can write it like this. Oh, actually, it's going to look like I'm just going to write it like this. So I don't want the notation to look weird. We already wrote it up here, so that's fine. Okay. So again, all of these are just notes that come from just looking at what the definition of the Laplace transform is. Of course, there's a few things we have to check. When does it exist? As we know, it doesn't exist for all functions. Can we determine For what functions does it exist? And then if we can determine that, how do we actually use it for simplifying differential equations, right? But for now, just looking at the definition, I think these are three important things to know. Right? Again, as a summary, it might not exist. Right? So the Laplace transform of a function might not exist because it's a limit, right? It's an improper integral. Right? Meaning that you have to be careful when you use the Laplace transform on a function. You have to make sure that that Laplace transform actually exists. You're not given for free that any function you have, the Laplace transform is going to exist. And then finally, if the Laplace transform exists, since we're evaluating from 0 to b all the variables t, you're left over with an expression that's an expression only involving the variable s, not the variable t. In other words, it's a function of s. Right? Okay, so that's just what the Laplace transform is. Okay. In the next video, we're going to start looking at examples of actually computing the Laplace transform, right, by hand. And then we're going to give you a theorem of the Laplace transform of a common set of functions that we're going to be using a lot.